Hello everyone. This is section 3.5, equivalent statements and variations of equivalent statements. I just wanted to show you that the weather has changed a bit at home, and this is just 3 days after my intro video, and we've got snow today, and so that's awesome. So we're going to get into equivalent statements here. So we've been talking about truth tables for a while within this chapter, and so we're going to get into what equivalent statements are. And so this is an example out of your book. This is a chart on the first page of this section, and it has to do with the four actors with the most Oscar nominations, and they are Jack Nicholson with 12, Laurence Olivier with 10, Paul Newman with 9, and Spencer Tracy with 9. And so from this, we can conclude lots of things from this diagram, this bar chart, but one of the things we can conclude from this bar chart is if the actor is Paul Newman, then he has received 9 Oscar nominations. That is an if-then statement, a P implies Q statement that we can conclude from that chart. And so what we want to do in this section is look at some variations of that statement. Okay, first of all, that is a true statement. Okay, that's what I mean by that. We can conclude that from that chart. That is a true statement. We're going to look at 3 variations of that. Okay, the first one is if he has received 9 Oscar nominations, then the actor is Paul Newman. Well, is that true or not true? Well, no, it's not true, because there's actually 2 of them that have gotten 9 nominations, right? So this is not necessarily true. Could be Paul Newman, but it could also be Spencer Tracy. And so that's not necessarily true, and if something is not necessarily true, then it's false. Okay, how about a different variation? If the actor is not Paul Newman, then he has not received 9 Oscar nominations. Well, let's look at the truth table of that. Well, not necessarily, because if the actor is not Paul Newman, then the actor could be Spencer Tracy, and he's also received 9 nominations, and so, again, that's not necessarily a true statement, therefore it is a false statement. Okay? And the last variation we want to look at is, if he did not receive 9 Oscar nominations, then the actor is not Paul Newman. Well, if he did not receive 9 Oscar nominations, then we could pick either Jack Nicholson or Laurence Olivier, either one, and they are not Paul Newman, and so that's a true statement. Okay, so we're going to break these down a little bit later in the section here and look at some of that and the truth tables of that and so on. But I just wanted to give you that as an example to kind of preview this section. So in this section, we're talking about equivalent compound statements. And so we've been talking about compound statements. They're made up of simple statements. So these are made up of the same one, just, P and Q, just basic statements. They have the same corresponding truth values for all true-false combinations of these statements. Okay, but here's the main point. If a compound statement is true, then its equivalent statement must also be true. So basically they have the same truth tables. If 2 statements are equivalent, then their truth tables must be the same. Okay, and so that's whether the statements are true, or if the compound statement is false, then its equivalent statement must also be false. Again, the truth tables have to be the same. Okay. Now, if that's not making sense from the definition, let's look at the truth tables for these, and I think that will make more sense. So, our first example here, okay, there's a question out of your book. It says, show that P or not Q is equivalent to not P implies not Q. Now, we've looked at these. We've looked at these in previous sections already, and so we're just going to compare them here. And so we're going to build those truth tables just like we have in the previous sections. Okay? And then we're going to use that result to write a statement that's equivalent to this statement. And so we're talking about how bills become laws and so on. So the bill receives majority approval, or the bill does not become law. That's where we're going to try to create an equivalent statement to this statement. Okay? So the first thing we're going to do is start with the truth table. And so our normal way we begin a truth table is with P and Q. P being true, true, false, false, and then Q being true, false, true, false. So we look at all the combinations. We've been doing this, right? We're going to add the not Q column because, again, the first statement here is P or not Q. So we need the not Q column, so we're going to add that. So again, every Q We just flip the truth value of it. And so if Q is true, not Q is false. If Q is false, then not Q is true. Same thing, Q is true, not Q false. Q is false, not Q is true. So we're just going through and flipping each one of those. Again, that's what the not does. Okay? Now we're going to create the P or not Q column and its truth values. Now, if you go back to our what we've been doing and look for the OR truth table, that's what we're applying here. So we're going to go back to the OR truth table and apply it to this. And so we're going to take the very first column, P, and we're going to take the third column, not Q, and we're going to use the OR truth table to combine those. Okay? And so if we do that, that's the truth table that comes out. If you remember back from our London, Paris example and so on, the only time the OR statement ends up being false is when it is false, false, when they're both false. Then the OR statement ends up being false. Every other time it's true. So that's the same truth table as we did before. Okay? Now we're going to take that and add another column to it here on the next slide. Okay? So the next slide, we still have the question there. Now we're going to add the not P column so that we can get into the second statement here and compare those. And so the not P column, we just take the first column and flip every one of them. So instead of it being true, true, false, false, it is now false, false, true, true. So we're just adding that not P column. And now we're going to add our last column to this truth table, and that will be the statement up above, not P implies not Q. Okay? And so we're going to take a not P column that we just created and then do the conditional statement truth table, combining that one with the third column, the not Q column. And so when we put those in that order in the conditional statement truth table, this is what ends up coming up. True, true, false, true. And if we look at that compared to the fourth column there, the P or not Q column, you'll see that the truth tables are exactly the same. Therefore, those two statements, P or not Q and not P implies not Q, those two statements are equivalent to each other. That's what we can conclude from that. So now let's answer the second part of that question, which was, really it's the main part of the question, that says to create a statement that's equivalent to the bill receives majority approval or the bill does not become law. We want a statement that is equivalent to that using these truth tables. Original statement, the bill receives majority approval or the bill does not become law. We break that down into its symbols, or break it down symbolically. P, the hypothesis of that statement is the bill receives majority approval. Okay. Q, now we take Q to be a positive statement originally. The bill becomes law. Okay. So then we're going to make it look like the original statement. And so the statement symbolically is P or not Q, right? Because the bill becomes the bill does not become law is not Q. Okay. Then, based on the truth table that we just created, this is equivalent to this statement. Not P implies not Q, right? We just did that with the truth table. So those are equivalent statements. Therefore, we can change the statement to be the same as this, and it's the equivalent statement. And so we're going to change the statement to words to be, if the bill does not receive majority approval, then the bill does not become law. That is the words expressed from that not P implies not Q statement. And that statement and the original statement are equivalent statements now. Okay? All right, let's look at example 2. This is just a real quick one. I'm just throwing this in for those of you that might still be a little bit confused about the whole negate thing or not. Most of you, I think, have that, but I just wanted to be sure. So this was example 2 in your book, and it says show that not P is equivalent to that little 3-line equal sign means equivalent. So show that not P is equivalent to just P. And I think some of you just look at that and say, well, sure. again, the negate sign is the same as a negative, and so the opposite of a negative number, or the opposite of a number, takes you back to the positive of that number. But let's go through a truth table here. So the original truth table for a P statement, any statement, is true, false. Okay, let's negate that. Let's add the not P column, and so we just flip them, right? So if P is true, then not P is false. If P is false, then not P is true. Okay, and then now we negate them again, because the negation symbol tells us to do that. And so we negate it again, and it becomes not P, and so whatever not P is, we just flip it the other way, and so it becomes true and false, which is equivalent, or the same truth table as P, the original one. And so therefore, we can say that P and not P are equivalent statements, and here's just a sentence that kind of is an example of it, real world example maybe. We can't not pay our bills. I know we're not supposed to use double negatives in English, but that's basically what this represents. Okay? All right, some other variations of the conditional statement, okay, or some variations. So back on our very first slide, we talked about variations of that, the Oscar nomination statement. And so the first one we're going to look at is called the contrapositive statement. So here's a definition of the contrapositive statement. And we kind of looked at this in section 4 of this chapter, but the conditional statement, it says here, is equivalent to its contrapositive. Okay? And so P implies Q, our normal just conditional statement, is equivalent to not Q implies not P. It says the truth value of a conditional statement does not change if the antecedent and consequent, or in other words, the hypothesis and conclusion, are reversed and both are negated. So you need to see that. That's what we did here. So we took the P and the Q, we switched their order, put Q first and P last, and then we put nots in both of them. We put the negation in both of them. Okay? That's the contrapositive. You switch the order and put nots in both. So the statement not Q implies not P is called the contrapositive of the original statement P implies Q. Okay? Now again, we kind of looked at that before, but that's the definition of the contrapositive. And we want to look at kind of the truth of that. Okay? So here's the truth table for a conditional statement. Okay, that's back from section 2, wasn't it? And so I just want to apply that to this statement here. So if we have P and Q, then really we're just copying that over here. True, false, true, true. Okay, but then I want to add that other column. If we take not Q, so if we just switch each of the Q's and then switched each of the P's and put them into that yellow table, the original conditional statement table, this is what the truth table would end up being. It would end up being true, false, true, true. And so those two statements do end up being equivalent to each other. And we could have done that out maybe in more detail, but that's the way it ends up getting to be when you put not Q implies not P. If we drew that out with all those columns in the table, this is the truth table for that. And so just showing that those are equivalent statements. Okay? So the original statement and the contrapositive are equivalent to each other. Okay, here's an example. Write the contrapositive for each of the following statements. So we're going to start with A. If you live in Los Angeles, then you live in California. We want to write the contrapositive of that. So the contrapositive, if we break it down into its pieces, from A, the P, the hypothesis is you live in Los Angeles. The conclusion, you live in California. And so if we switch those and put in nots, then here's the contrapositive. If you do not live in California, then you do not live in Los Angeles. And that's a true statement, right? You can't live in Los Angeles if you don't live in California in the first place. Now, if we go to part B, it says if the patient is not breathing, then the patient is dead. Now, you have to be a little bit careful here because the hypothesis statement here, the patient is not breathing, already has a not in it. And so if we not that, if we negate that, we would have to take the not out. And so our original hypothesis should be the patient is breathing and the patient is dead is the conclusion. And so if we translate that into not Q implies really not P, because the P was already knotted, had a negation in it, then the contrapositive is if the patient is not dead, then the patient is breathing. Okay? And C, the last statement down there, if all people obey the law, then prisons are not needed. And so we break it down into the hypothesis and conclusion here. And so again, notice that conclusion has a not in it, so be careful with that. So our P is if all people obey the law, so all people obey the law is the hypothesis, negate the Q already has a negation in it, so the Q by itself would be prisons are needed. And so if we translate that into the Q implies not P in English, then if prisons are needed, then some people do not obey the law. Remember that recall there is remember that in order to negate all, then you can put some, few, whatever, as long as you come up with some that make it to where it's not a true statement. All right. Other variations. So we have the contrapositive, but then we have other variations of the conditional statement. And there's two other ones called the converse and inverse. Okay. So here's a chart from your book that shows all of them now. So we have the original conditional statement, P implies Q, if P then Q. We have now what's the converse, and the converse essentially just switches that order. Okay. And I'm going to go back to our original slide of the Oscar nominations to see how this order switches here in just a minute. But the converse switches the order. That's all it does. The inverse keeps the original order, but then puts nots on both of them. Not P implies not Q. That's the inverse of the original statement. And the contrapositive, as we were just looking at, switches the order and puts nots in them. And so you need to keep those three separate from each other from the original statement. Let's go back to our original slide and take a look at that. So here's our original slide from the beginning. Okay, and there's our first P implies Q. If the actor is Paul Newman, then he's received 9 Oscar nominations. Okay, if we look at the first variation right there, if he has received 9 Oscar well, that's the last part of the original, right? And so if we put that first and then put the first part last, we've just switched the order. And so that would be the converse. So that first statement right there, first variation is the converse because we just switched the order is all. Okay? And if we look at that, if he has received 9 Oscar nominations, we said it's not necessarily true. And so the converse is not equivalent to the original because it's actually false. Okay? Again, if something's not necessarily true, then it's false. Okay, so the converse is not equivalent to the original. That second statement, if the actor is not Paul Newman, then he has not received 9 Oscar nominations. Well, if we compare that to the original, it's the same order. We just put nots in both of the pieces, right? And so that would be the inverse statement. And the inverse statement, as we see here, if it's not Paul Newman, we already said, then that's not necessarily true. And so the inverse is not equivalent to the original statement either in its truth table. Okay? And if we look at the last one, if he did not receive 9 Oscar nominations, then the actor is not Paul Newman. Now we have switched the order, and we've put nots in both of them. Okay? And so we've already talked about this. This is the contrapositive statement. And we've already seen that the contrapositive has the same truth table as the original statement. And so the contrapositive is equivalent to the original. Let's look at some more examples of that. Here's example 4 out of your book. Okay? The original conditional statement is, if it's a BMW, then it's a car. That's a true statement. Okay? The converse, remember, it just switches the order. If it's a car, it's a BMW. Okay? It just switches the order. And that's not necessarily true. There's lots of cars that aren't BMWs, right? And then the inverse, if we look at the original statement, we keep it in the same order, but we put nots in both of them. If it's not a BMW, it's not a car. Well, if it's not a BMW, it could be an Apple or a Dell or you can take it, anything, really. It's not a car. It's not necessarily true. You could put something in there to make that true, but it's not necessarily true. Okay? So we're just emphasizing that the converse and inverse are not the same truth table as the original statement. This is a great chart out of your book, and I'd kind of like you to focus really on the top first. And so if we look at the top part, we have the original statement, the original conditional statement, P implies Q. Its truth table is true, false, true, true. If we compare that all the way over to the contrapositive, that we've already done the example for, not Q implies not P, it has the exact same truth table. Those are equivalent statements. Okay, but if we look at the bottom half of this chart, if we compare the original conditional statement to the converse, they're different truth tables, they're mixed up. And if you compare it to the inverse, they are mixed up. Okay, the original conditional and the inverse are mixed up, and so they're not equivalent either. Okay, however, do notice that the converse and inverse have the same truth tables, and so they are equivalent to each other. We're not really going to use that one, but the conditional and contrapositive we will. The fact that those are equivalent statements. Okay, so just another example there and a great chart from your book to look at. Another example, example 5. The following conditional statement regarding state and national elections in the United States is true. If you are 17, then you are not eligible to vote. Okay, this comes from a 1971 when voting age was lowered from 21 to 18 with the ratification of the 26th Amendment. Okay, the question is, write the statements converse, inverse, and contrapositive. I believe this was kind of an outcome of the Vietnam War, that if you're 18, you could go fight and serve your country, but you couldn't vote. It didn't make a lot of sense, and so that got changed in 1971. So let's look at these statements, okay? So first of all, again, we have to be careful with this one because it's got a not in it already. So we're going to take the statement to be, the hypothesis is you are 17, and we're going to take the conclusion to be you are eligible to vote, okay? This original statement happens to have a not in it, so we need to be careful with that. But that's our hypothesis and conclusion right here, okay? So we're breaking it down right here, and the original statement looks like this. If you are 17, which is the hypothesis, then you are not eligible to vote. So really the original statement here is, the statement that they gave us is P implies not Q, because it has a not in it already. All right, so let's look at this table of all of the options. So the original statement, P implies not Q. The original statement is if you are 17, then you're not eligible to vote. Okay, let's compare that to the converse. Well, the converse just switches those pieces, right? Switches the hypothesis and conclusion of the original statement. So our original statement was P implies not Q, and so we switch those. Not Q implies P. In English, that would be if you're not eligible to vote, then you are 17. Well, that's not necessarily true. There's lots of other, you could be 16, you could be 15. There's other reasons why you can't vote. Like if you are convicted of a felony, I believe you cannot vote, and other things. So, okay. Then let's look at the inverse. The inverse, remember, puts a not. Keeps it in the same order, but puts a not in both of them. Okay? And so if you look at that not P, that's putting in a not, implies, and then not Q, because again, the original statement already had a not in it. Which simplifies, if we take those two nots, it would become a Q. And so really what we're looking at is not P implies Q. And so if you're not 17, then you are eligible to vote. Okay? That's not necessarily true either. Again, it could be the old felony thing or whatever. Okay? If you're not a citizen of the U.S., you're not eligible to vote, and so on. Okay? Last one. Contrapositive is you switch the order of the original and you put a not in both of them. And so if we switch the order, that would be not Q implies P, and then put a not in both of them would be a Q implies not P. And that would be if you are eligible to vote, then you are not 17. And that would be a true statement. Because if you are eligible to vote, you can't be 17. You can't be 16, but you can't be 17. Okay, so there again we show that the truth table of the contrapositive is the same as the truth of the original statement. Okay? Here's just a sidebar on the end, math and literature. Alice in Wonderland is a huge book that has to do with math. You may not realize that at all, and I don't want to ruin it for you if you don't want to think of it in terms of math. But it was written by Lewis Carroll. That's his pen name. It's actually Charles Lutwidge Dodgson. He was actually a very famous and respected logician and geometrician. It's actually considered to be his reaction to non-Euclidean geometry, it's called. And I don't want to get into all that, but non-Euclidean geometry is basically geometry outside of free space, or in free space compared to what we normally do in geometry in high school of just kind of on a flat surface and so on. And so non-Euclidean geometry would be used by like a pilot, because if a pilot flies from Florida to New York to LA and then back to Florida, if that's his path, well, he's flying across a curved surface, and so it's not on a flat plane. Okay? And so things kind of go weird, like there's not 180 degrees in a triangle anymore, and other things. And so the whole confusion of Alice in Wonderland is Lewis Carroll's kind of concept of that non-Euclidean geometry. So if you want to check that out, it's called the Blitzer bonus on the bottom of page 169 in your textbook. You can go play around with that and just read what it has to say there about all the inverses and contrapositives and so on of Alice's statements in there. Otherwise, you just need to head off and look at 3-6, because actually they're combined. 3-5 and 3-6 assignments are combined into one. And so check out the video for 3-6, and then you can work on that assignment.